Screencast 3, it continues talking about limits, and here we're going to be talking about 1.3 in particular, discussing one-sided limits. So previously we just learned that the limit of a function is equal to the value the function is converging on from both sides of a. And we can also find the one-sided limit of functions by approaching a from either the positive or the negative side. And again, positive, negative side, I mean either the side greater than a or the side less than a. Now, how do you know which side to approach the limit from? Well, it's specified by a superscript next to a. So if the question is asking you to approach from the positive side, it would be written like this: the limit as x approaches a with a superscript plus sign of our function. And if it's the negative side, it will have a superscript negative sign right next to the value. So, for example, let's find the limit of our function square root of x approaching from the positive side. Now you'll see this is very valuable because the function is not defined when x is less than 0. So only a one-sided limit can be applied when x approaches 0. So if x was approaching from the negative side, this function wouldn't be defined, so that wouldn't be possible. By inspection, we can find that the limit is 0. Taking the square root of 0 equals 0. So one-sided limits can also apply to discontinuous functions, and you might ask, what is a discontinuous function? And that's a very valid question. I'll explain it by using an example. So far we have looked at functions that are defined by one mathematical relationship. So it'll say f of x equals some function. So whether that's a polynomial or whatnot, it will be a function with x as the variable. But this isn't always practical for real life situations and relationships that calculus usually compares. So, for example, if we wanted to define a function for the cost of mailing a parcel across Canada, it will depend on its size. So one variable is the cost and the other variable is the size. They're both interrelated and dependent on each other. So you'll always have a minimum cost, and I think it's about 50 cents to mail a letter. And as the weight of the letter increases, the cost will also increase. So cost, let's say m is mass, it'll be the minimum plus just some random function that I use as an example here. For example, plus 4m. So m, let's say it's measured in kilograms. And also, as the volume increases, as the size of the actual parcel increases, the cost is also going to increase. So x, let's say that is the volume measured in centimeters cubed. And so we'd have another function where cost is dependent on the volume. And as our parcel continues to grow, we'll have to eventually reach a maximum. I mean, Canada Post can't send parcels that are infinite size and infinite mass. So, for example, they may say after 1 kilogram and 500 centimeters cubed, we can't send the parcel. So it's too big to be mailed. So that means that our mass must be less than 1 kilogram, and our volume must also be less than 500 centimeters cubed. However, this function that we have used up here, or any other function like a polynomial or any function that we've seen previously, it's defined for all values of x. So this function is going to exist and can be calculated where x is negative infinity all the way up to positive infinity. But if we wanted to use our mail example, that wouldn't be very practical because we know we can't, not only can we not send parcels of infinite size, we can't send parcels of negative size either. So we have to define the variables. So that's where you say that the domain of the function is restricted. So the domain of a function can be defined by, say for this example, if we wanted to have a function where x is less than 1, we're going to use this relationship. Now for the same function, when x is equal to or becomes greater than 1, our relationship changes to x minus 2. So let's graph this. What does this look like when we see a function, a discontinuous function that is presented to us like that? So let's graph this. So here we have our y-axis, our x-axis, and here in red I've just highlighted where x equals 1. So on one side of the function, the side greater than 1, we're going to have a different function, and on the side that's less than 1, our function is going to look different. So let's graph one of these. Let's graph, say, where x is greater than or equal to 1. So this function, x minus 2, is this line. So line with a slope of positive 1 and a y-intercept of negative 2. However, we've said that our domain has to be greater than or equal to 1. So anywhere that our function is less than 1, it's not going to exist. So we can get rid of it. Everything our function looks like less than 1. And when it equals 1, our function is defined. So we can use this dot or a closed circle to represent that this function is defined at this point. Now what about our second domain? When x is less than 1, we have this line, x plus 4, and it's graphed like this. However, when x is greater than 1, our function doesn't exist there, so we can get rid of that. And when x equals 1 on this function, it doesn't exist. It's not defined. It's only when x is less than 1 does this function exist. So here we're going to use an open circle to represent that it's not defined at 1, but anywhere less than 1, it is defined. So a function that is not continuous at all values of x, in this case, in this example, it's at x equals 1, is said to be discontinuous. So this is a discontinuous function. And you'll see that another way of describing it is the function jumps at x equals 1. And you jump from one spot on the function to another spot altogether. And this right here is called a discontinuity. So there are many examples of discontinuous functions, and here we have a cubic function and a quadratic function, and here the jump or the discontinuous point would be point 2. And here we've got a number of discontinuous points where even when you're traveling along the point, if all of a sudden you reach -2, your function will be 1, and then after that it jumps back down to continue. And here we've got this quick jump as well. And another one which I didn't mention earlier was anywhere where there's an asymptote. So this example where y equals 1 over x, it's not defined at x equals 0. So here we have a discontinuity as well, right at x equals 0, because here it goes up to positive infinity, and then down here it'll go all the way down to negative infinity. So they'll never touch each other. So to find limits and one-sided limits of these types of functions, we can there's two ways. We can either, if we're given a graph and we have a visual representation of our function, we can follow the function along the graph from the specified side. So for example, if they say find the limit as x approaches 0 from the positive side, we can follow our function from the positive side and see where we end up as we approach 0. And in this example, we approach 1. So as we approach 0 from the positive side, we converge on positive 1. So what if we have to find the limit from the negative side if they ask for a negative limit? We do the exact same thing, but we start on the negative side, and our function converges on -1. So as we approach 0 from the negative side, we converge on -1. So the one-sided limit from the negative side is -1. So this is interesting though, but what if we need to find the limit of this function at 0? be that positive or the negative side. Now when they don't specify a side, that means that the limit must equal from both sides in order for it to exist. So because for this example, the limits from the positive side and the negative side converged on different values, the limit at 0 does not exist, and we notate that as DNE. So to put this into general terms, in order for the limit as x approaches a to exist, both of the one-sided limits must be equal. So the limit from the positive side must equal the limit from the negative side, and it must be the same value, whatever that value happens to be. If this is true, then the limit at a, in general, from both sides, equals the existing limit. Now, if both of the one-sided limits are not equal, the limit from the positive side does not equal the limit at the negative side, this means the limit at a does not exist, DNE. What if we're not given a graph? So the second method of finding the limit of discontinuous functions is to specify the domain. So we have this function that we talked about earlier that we just graphed, but what if we're asked, what's the limit of as x approaches 1 from the positive side? So we must determine where the function is defined when x is greater than 1, because we're approaching the limit from the greater than 1 side. And we can tell that x is going to be greater than 1, then this function is used, so x minus 2. And now we can just inspect that, and 1 minus 2 is negative 1, so the limit from the positive side is negative 1. Now before you go on, I just want to leave you with the sign. The limit as x approaches 1 does not exist, and I want you to prove this to yourself before you go on and do the homework. So the limit from the positive side does exist, and it's equal to 1, but the limit as x approaches 1 does not exist. Prove it to yourself. So take a moment, pause it, and figure that out. Now you can complete problems 1, 2, 4 ACE, or more if you would like, 5, 7, 10 AC, and these are on pages 27 to 29 of your textbook. And the next screencast will talk about 1.4, where we're going to use our limits, what we learned about limits, and we're going to apply that to what we learned in 1.1 about tangent lines.